Welcome to my talk about cybersecurity. So today we will focus on how to quickly detect top security vulnerabilities in your software. And in this presentation, I will try to especially focus on the software development phase. So for those of you who are already familiar with MathWorks tools, you know what kind of tools we have. And in this presentation, I will especially focus at the software layer. And so we will try to answer questions in this presentation, like what is cybersecurity and how does it relate to safety? What are the current standards for code verification and their impact? How to simulate an attack? How can we assess the risks? And how can we mitigate the effects of attacks? So let's start with a small example. So here you have a model of an electromechanical motor that is made in the middle of a controller and on the right-hand side of a plant model. And the signals that are coming out from the plant model are driven via a CAN bus to the controller. And here you can see that when the system is switched on, you will be able to set the velocity with the set point knob, and the system will be able to follow the required velocity correctly. But then suddenly, as you can see in the upper left corner, there is an attacker outside of the environment that we will now switch on. And then when this attacker enters the system, you can see that you cannot set the velocity correctly anymore, and that the system is completely working in an unknown behavior. So here, even if the attacker stops the attack, you can still not take control of your system. To recover, you will be able to switch off your system and then switch it on again. And in this case, you will be able to recover from the attack. But as you can imagine, this is not a good use case, because if you are, for example, in an aircraft, if you need to switch off the aircraft to survive the attack and then restart it, that's perhaps not the best solution. So here, that's an example of how you can simulate such attack, indeed, before going to the state where you implement your code onto the target. And we will discuss this during this presentation. Okay, so here we have some statistics. So these are some data collected out of incidents that occurred in the automotive industry. And you can see that there are at least 60% of the issues that are coming on the left-hand side with the blue bars from embedded systems. The rest of the issues here, yeah, perhaps the color, it's not easy to see it, but it's gray on the right-hand side. And these are attacks that are coming on the server side. But with that, we can already see that most of the half of the attacks are coming on the embedded system themselves. You can see that, for example, the keyless entry system is one of the preferred way in order to access the control of a car. So this technique is indeed very useful. You just come next to your car. You don't need to put the key in the lock to open it. That's very useful. But then attackers can take advantage of this. And here, for all these vectors of attacks, this is not just a sum of all of them that will give you this number, but you can have a combination of these different attacks. That means that at the same time, you can try to use the keyless entry system, plus, for example, the engine control unit or the telemetry control unit. These are different ways in order to do that. And in the case of a car, for example, you have such a system like a gateway that is there in order to protect safety applications in your cars from, for example, the infotainment system. But an attacker could perhaps take advantage of such system in order to enter from the infotainment the information that you can get in the telemetry or something like that, to steal data or to take control of the car. Okay, so now, what are the common challenges that we have to face when it comes to embedded cybersecurity? So here there is a lot of common questions that are often raised. Like, for example, there are so many aspects for us, the engineers, to consider, like how to satisfy security standards and guidelines, but also how to measure security, how to detect vulnerabilities early. That's one thing I will try to convey today, is to explain to you that it is quite important to shift all the testing phases to the left of the V cycle. We will see that right after, so that you can detect errors early and you will reduce cost on eliminating these errors. Also, how to limit time and efforts by working in teams, for example. Do you need specific tools for that? So you will see that if you want to do dynamic testing onto your system, it will be quite cumbersome because you have an infinite of possible test cases. So there is another technique to do that using static analysis tools. So these are the kind of tools we can use for that. And also how to handle some legacy code that you have, because for sure you would like to reuse what you have already developed in the past, but then perhaps you will have to update this code if you find a failure in it, and so on and so forth. And also how can we build an expertise out of all this process? And there are much more questions that we can discuss also. But we'll try to answer some of these questions. So let's start with what is cybersecurity and why safety is not enough. Here I will try to explain to you what is the relationship between security, safety, cybersecurity, and why is it so special. So we will try to start with a common definition so that we all speak the same language. So you can see in blue, there is the environment into which the system is evolving. So the system can be the car, and in the environment, for example, you will have a hacker, or you will have other cars or something like this. So indeed, when we would like to define safety, it first comes with a fault. So safety is linked to the fact that there is a fault in the system. Like, for example, if you are doing collaborative robotics, you will have a human being interacting with a cobot. And in this case, it can be dangerous if there is an issue with the cobot. Then it can result in a safety problem, creating a failure. Failure could be that the human being will be hurt, injured by the robot. And that's something we do not want, for sure. So that's the definition of safety, protecting the environment from the system. And then we have the definition of security. Here, security, it's about protecting the system from the environment. So in this case, you can have an attacker, like we have seen before, that is outside of the system. And then, if the attacker can overcome the security wall that you have there, this will create a new behavior in the system. And you are not aware of what this new behavior will do. You have no clue what impact it will have onto your system. What can come out of this is that you will have some data that will be stolen by the attacker. So the integrity of your data will not be safe anymore. You can have data that can be modified, stolen, and so on and so forth. And then what this new behavior can trigger as well is that it can trigger new fault that will have also an impact on the environment, but also the new behavior can indeed give control to the attacker. I'm sure you have already seen this example of the Jeep car that was attacked by two guys. They could control it from their laptop, okay, which is quite dangerous at the end. So security prevents abuse and safety prevents hazard. And cybersecurity is directly linked to that. So during this presentation, we will base our flow on the V process, on the V model as well, which is quite used in the industry. And here, when it comes to safety, so we focus on design for reliability and failure. So that means we already know what are the safety criteria we would like to apply onto the system. Like in the case of the cobot, we don't want the cobot to hurt the human being. Then we can put the focus on what is known. Okay, so we have specific test cases that we have created in order to test the system. And then we do rigorous testing as well. When it comes to security, so here we have to design the system so that it can resist malicious attacks. So that's where we have to do static analysis, for example. And also we have to cover what are the unknowns. As you have seen in the example before, there are use cases when an attacker will enter the system. You don't know what will happen within the system. So that's why we have to handle this part. And for sure, we also have to monitor and update the system regularly, because if you find out that there is a failure in the system, you will have to do an update of it, and so on and so forth. And for this, we will base this presentation on the V model. And as I mentioned, I will especially focus on the software implementation part rather than on the other sections. Okay, so now that we have a common understanding of the challenges that come with security and that it is different from safety, let us move to what can model-based design do for cybersecurity. So here, there are various techniques that can be applied at each steps of the V model. So for example, if you go at the system design, you can already design your system to take possible threats into account and to create components that will be indeed units that are not directly coupled to other components. So for that, you will do what we call high cohesion and low binding. High cohesion, that means that all what is related to the component is within the component itself, and it does not rely on to data that are outside of the components. And low binding, that means that the interfaces are clearly defined between the components so that the minimum required amount of data is shared between the components. That's also useful when it comes to update your system. In case there is one fault in one component, you will be able to do an upgrade of this component only. Then we can do some analysis on the software design. So here you can already verify that your model is following some specific standards and guidelines, like MISRA guidelines, for example. Oh, I don't know what happened yet. It just disappeared. Yeah. The system is under attack, yes. So feel free to have questions in the meantime. So I plan to have them at the end, but yeah, feel free to ask questions. There is a Windows update right now. So yeah, perhaps in the meantime, I can give it a try to go on without slides. It will be a bit freestyle, but let's see. So yeah, we were talking about the V model. And then, what comes then? It's difficult without the slides. Yeah, so basically I can jump to static code analysis. So yeah, there is one thing that often comes is that, so you have seen in the model I had, then the goal is to generate code out of the model and deploy it onto the target. And there is one thing that often comes is that, okay, when we verify the state at the model level already, why do we have to verify the generated code as well? Because if it is stable and correct within the model, it should be also the case in the code, because the code generation process is a faithful translation from the model to the code. The answer is no, because you can see it in a demo I have on my demo booth. So it's not a demo about cybersecurity, but it's a system. You have an algorithm that is done for the electrocardiogram measurement and signal processing. And this algorithm, you can design it in your model. But then you need to deploy this onto a hardware that is made of peripherals. You have several peripherals on it. And when you do that, you have to integrate the code for the peripherals with the code that has been automatically generated. That's why you cannot only verify at the model level and not at the code level, because during the phase of the deployment of the code, there is an abstraction layer for the model, and then you will get at a lower level of abstraction for which you will integrate with hardware peripherals. And in this case, you have to verify that the code that is integrated with the generated code is working correctly. That's why you have to verify the code. And also another pragmatic reason for that is that standards require it. So if you want to certify your product, you have to go through this step of verifying the code, because at the end, the code is running onto the target, not the model. So these are important things to keep in mind. And for this, there are tools in order to analyze the code. And at MathWorks, we have a tool called Polyspace that allow you to do that. So it will do statistical analysis of the code and written code and automatically generated code. And with that, it will do a formal verification based on mathematical proof that the code is correct. So if your code is safe, it will prove you that the code is safe. And the advantage is that you don't need to provide any input stimuli to your code, and you don't need to run the code. All this will be done statically. Okay. Yeah, it was earlier than that, but okay. Yeah, so yeah, I was at the right one. That was this one I was explaining right now. So yeah, here, that's what I mentioned before. So you generate the code, but then you integrate this generated code with code that is meant for hardware peripherals, for example, or also operating systems. And then you need to verify at this level that the code is safe and correct. And these are the steps I mentioned just before. Okay. Good. So what can we do here? So if we talk about verifying the code, step one is to handle the knowns again, okay? And for that, we can follow the coding standards. So here you have some of them that are there. I'm not a specialist in standards, but these are the list of those that you can rely on when it comes to security and cybersecurity, also cryptography. But we also want to check the robustness of the system. And here we have to answer questions like these ones, for example. So do I have a division by zero in my system, which will be really harmful? Do I have underflow, overflow of data? Does the system always work? Can I have race condition when it comes to access specific data? So for example, two threads that tries to compete for the same resources, and then the system is blocked, and so on and so forth. So this, as I mentioned before, cannot be done dynamically. You cannot create all test cases in order to verify your system dynamically, but you have to do this statically with formal proof. Okay. Now, we can already apply some of these verification steps at the model level. So here, for example, you have the model advisor. That is a tool that allows you to already verify at the model level that you are following specific guidelines like MISRA-C, CERT-C, and so on and so forth. And also so that you can verify what I mentioned before, the division by zero, the data overflow, and this kind of things that could occur. So at the end, the only verdict will be on the source code. So here we can already do that at the model level. But as I mentioned, it can be that in your model, you did something wrong. If you have a bad model, you will get bad code. So that's why it is also important to verify the code. And by doing this step of verifying the code, you could perhaps see that you did a mistake in the model. And then you go back, you correct the model, you regenerate the code, and then the correction is applied, and your code is correct. That's how you do, basically. Okay. So now, yes, secure coding guidelines. So here, the thing is, there are some rules that you have to follow so that security is applied correctly. You cannot only have security engineers working on the security tasks. This is the work that everybody has to do, indeed. So it starts already with the developers. So you have to train the developers to use best practices and guidelines, as I showed before, to avoid some specific errors. Also, the workload should be shared among all the people from the team, and you should try to shift the testing phase to the left-hand side of the V-cycle as much as possible to detect errors early. And then, yeah, you have to do static analysis to be sure that your code is correct and there is no mistakes in it. And then at the end, all of this should be automated. That means you should have CI/CD installation. So for in order to test every time, for example, a colleague create a new version of the software, you need to be sure that this software is safe and robust. So you will send it to the continuous integration, continuous delivery server so that the code is generated, the code is built, compiled, and so on, even downloaded onto the target and see if this works fine. This is to cover both the unknowns there and the knowns here. Okay. I still have some minutes, good. So our method of choice for code level security verification is called static application security testing. That's how it is called in the world of cybersecurity. And this method, as I mentioned, is implemented in our polyspace tool and based on analytical proof instead of dynamic testing, which is the big difference. And as I mentioned, with static analysis, indeed, you don't need to provide input stimuli to your code that you need to test, and you do not need to run it as well. Okay, so here you have an example of polyspace and the dashboard, how it works basically. You have here indeed the analysis of the code that says that 93% of the code is correct. So you can be sure this has been mathematically proven by doing an analysis of the control flow and the data flow that your code is correct. And then you can see that you have some examples, like for example here in red. So what is in red means that here you have an error and you definitely need to correct it. Otherwise your system can have some faults. And so there are different verification steps, like for example gray. Gray, that means that you have a branch condition that is never reached. So that means you have some dead code. And you have to correct your algorithm so that it is behaving the right way. And here you can see also that the advantage of static code analysis is that it will do a full coverage of your code. So you will have 100% full coverage, things that you cannot get with dynamic testing. If you have an infinite amount of test cases, you will never reach 100% full coverage. Here, that's an example when indeed at the model level, we have already applied the check I showed you before when it comes to verification of the code. And you can see that indeed when the modifications have been applied at the model level, when it comes to the code level, where you will also integrate some unwritten code for the peripherals and so on, then you already get 50% less CERT-C, in this case, violations. And you will add some new violations based on this unwritten code that you have integrated in your system. But you would have already removed half of the fault, which is an advantage. And here are the key takeaways for my presentation. So first, the goal is to achieve higher security level by already shifting all the testing phases to the left-hand side of the V-cycle. Then the goal is to prove the absence of errors within the code by doing static code analysis. And then finally, we have to work in team so that the workload is shared. And also we have to automate all this verification process so that every time someone is committing a new revision of the source code, everything is correct. And that's a summary slide about cybersecurity, how to do it. This is what I presented to you today. And now we still have 4 minutes if you have questions.